Let's suppose we have a rocket with a transfer function of g equals 10 over s squared. So that's a transfer function. And then we're going to call Sisotool for this. And if we look at our Sisotool, we notice that we have 40 dB per decade decay, and we have an intercept at 0 dB at 3.16. That's the square root of 10. Okay, if I've got 10 over over s squared in the forward loop, then my root locus is going to be given by KRL times GH, H is 1 in this case, when S equals J omega. Or I can say that my K root locus, my G is 10 over S squared when S equals J omega, and that has to equal a magnitude of 1 at an angle of 100 plus or minus 180 degrees. So when I substitute my J omega, I will get KRL over 10 over J squared, 1 over omega squared. J squared is minus 1, and that takes care of the angle. So my angle is minus 180 degrees, and therefore my angle of 180 degrees puts me on the root locus for... Now if I look at my root locus gives me a box. It's given me a box right here at 3.16. That equals 3.16. So if I draw my phasor from the origin to 3.16, like so, that will give me what we said was LP1, L pole 1, where we have two poles from the origin, and LP1 is one of them. And it has an angle of 90 degrees in the denominator. So 2 of those gives me my J squared, which is my 180 degrees, satisfying the angle condition. Now the magnitude condition, we know that KRL 10 over the magnitude squared, which will be KRL 10 over LP magnitude squared, that has to be equal to 1. Well, if that's the case, and I know the root locus closes these roots for a gain equal to 1. This first box you get equals K RL equal to 1. That's what you get out of Sisotool. So therefore, I can say that KRL is equal to LP squared over 10 from this. If KRL is equal to 1, then my LP squared is going to equal the square root, magnitude of LP is going to be the square root of 10, which is 3.16. I notice that my 0 dB, that's 3.16, is going to take me right down there at 0 dB, right there, going across 3.16. So I have Bode slope of 40 dB per decade, or minus, so this is going to be minus 40 dB per decade. That's 1 over s squared, be dB per decade. And at the 0 dB crossing, I have omega squared, and my numerator, that 10 and my omega squared are equal, so the omega must be the square root of 10, or 3.16. So everything seems to fit. This is just showing you what the root locus gives you. The time response can be found under analysis response to step command, and that should give you time response, which doesn't look very good. It's very oscillatory. This is a neutrally stable system. Any second order system in space will be neutrally stable. So if I were to add an actuator, here's the shorthand form, 10 over s plus 10, and my open loop transfer function then would be 10 over s plus 10 now times 10 over s squared. So in shorthand, that's how it would look. And then if you wanted to look at Sisotool, you would see that the system would become unstable. And again, if I were to look at this, I would see my phase margin is minus 17 degrees. So when I cross the 0 dB point, where the hand is right now, I see that I'm already past 180 degrees, so I have a negative phase margin. That means the system is unstable. And if I look at the root locus, I can see that that is indeed the case. If I were to blow up the root locus a little bit, the actuator I see has taken my pole at the origin. When I close the loop on it through a gain of 1, it is sent it into the right half plane. So let's suppose that I put some lead in for that actuator, and I'll pick 4 over S plus 1 over S plus 4. That'll put the 0 closer to the origin and give me some lead on that actuator. So if I were to run this on MATLAB with Sisotool, and now look, and I would see that, again, if I close the system with a gain of 1, it looks like I have a root right on the j omega axis. But if I go over to my Bode plot and see that if I lower the gain slightly, I'm going to get some phase margin. I can maximize the phase margin by lowering the gain to give me a crossover frequency of about 1.6 radians per second. So at 1.6 radians per second, I'll maximize my phase margin, which looks like it's going to be 27 degrees. And again, the MATLAB Sisotool plot is giving me all this. And the crossover frequency is going to be 1.62 radians per second. And that gives me an approximation of the system closed loop bandwidth. So I would expect a closed loop bandwidth of around 1.6 radians per second. And if that's good enough or not depends on what you're doing. My gain margin over here is where the phase margin crosses 180 and stays below 180. So my phase margin is going to be listed here at 15.6 decibels at 5.1 radians per second. 5.1 is this frequency right here, and 15.6 dB is how far below the 0 dB I am. So if at 180 degrees I have gain margin positive gain margin and positive phase margin give me a root locus that's acceptable. So I can look over here in the root locus program and see that indeed I do have a acceptable root locus. My actuator pole is moving to the left of an odd number out towards net minus infinity. I have a pole going to a 0. That's the lead, or the lead S plus 1 over S plus 4 I have right here. And then that lead has pulled the double pole at the origin in before it eventually goes back to its unstable point. So that's how you would do the system with the operator with Sisotool.